Hello everyone, I'm Mahnur and today we will be starting off with the second unit of A-level physics, that is, kinematics. Now, when it comes to this chapter in its entirety, it's nothing but the study of motion. More specifically, it's the study of how you can describe motion in more ways than one, especially when it comes to a variety of different types of motion. This is quite practical when you think about it because around our world, we find many kinds of moving objects, whether that's a regular car moving along a road or a rocket ship launching up in space. No matter what, the study of motion is what we're dealing with in kinematics. We'll be dealing with factors that affect motion or factors that cause motion in the next unit that follows, which is basically dynamics. So it's clearly obvious that an understanding of dynamics is only possible if we know how you even describe motion to begin with. Now, if you're coming from O level physics, you might be familiar with this already. This is a topic that you find there, basically, you've already done it if you think about it. But over there in O level physics, things are quite surface level. You don't really dive into these concepts of kinematics beyond them just being definitions or just equations that you apply directly to a question. AS level physics in that regard is quite a different playground entirely, because here we'll be taking those same fundamental concepts and applying them to far more complicated scenarios. So it's very important for us to build a very strong foundation at the very beginning, which is why we'll be starting off with revisiting some of those fundamental definitions first and foremost. Again, it might seem as if these are concepts that we're too familiar with already, they're quite straightforward, but I want you to understand these from the very basics first. Once we have this strong foundation set, we can immediately build towards far more complicated scenarios that will definitely come later on. So, if we talk about the simplest scenario out there, let's consider the following object. Let's say you have this little observer over here, starting their journey from this point A all the way to this point B. And let's suppose they're feeling fancy and they cover this kind of a twisty, curvy kind of path. Now, in doing so, suppose that a friend of this observer wishes to understand this path better. More specifically, they're interested in knowing how long this path is. That's nothing but a measure of the length of this path, in which case, what they're measuring is what we call distance. The symbol we'll be using over here is going to be the lowercase d, and we define it a bit more formally as the length of the path covered by a moving object, right? And since there's an emphasis on the path in itself, you can clearly then predict that the same observer could very well evaluate a different value of distance entirely just by taking a different path. Suppose the same observer covers this kind of a path instead of the red one. So here you can clearly see that with the same endpoints, the distance is entirely different purely because a different path is taken. And so we must highlight the fact that distance is a quantity that depends on the path itself. Now let's suppose a different scenario where the same observer wishes to go from A to B, but instead of choosing these strange sort of paths, the observer instead chooses to move in one straight line. In that scenario, the observer is picking the shortest path that they can, starting from a point A towards a point B. This is where we don't just talk about distance anymore, but rather a new quantity that we call displacement. Here the symbol we'll be using is going to be the lowercase s, used just by convention, and we define it as the shortest path covered by a moving object, starting from, of course, one point and ending at the other point, from one point to another point. Now here notice how there's less emphasis on the path itself because this is merely the shortest path that you can take, for which is entirely unique as we see by this blue arrow that I've highlighted yellow. Instead, there's an emphasis more on the motion starting from one point to another, which means that displacement is a quantity that only really depends on the endpoints. In other words, the shortest path itself would only change only if you were to change the spacing between A and B. It wouldn't change no matter what other path you take, because the shortest path is going to be the same. Now, after having defined distance and displacement so carefully, it's important for us to highlight a fundamental difference between the two. Distance just so happens to be a quantity that's a matter of length. Distance is a quantity that clearly has just a magnitude that you can ascribe to it. Therefore, distance we describe as a scalar quantity because it only has a number you can ascribe to it. On the other hand, displacement is a quantity that has a sense of directionality to it because it's always starting from one point and ending at the other. So not only is there a magnitude ascribed to it, but also a direction. In that regard, displacement is what we consider as a vector quantity. Great. Now that we've highlighted these two quantities that help us understand the shape or the length or the pattern of a particular path, another way we can study the path covered by a moving object is seeing how it changes with respect to time. In that regard, we introduce two new quantities, speed and velocity. Speed is what we define as the rate of change of distance. And its formula is in that regard quite straightforward. It's simply a measure of the amount of distance covered per unit interval of time. On the other hand, velocity is a quantity that's defined as the rate of change of displacement this time. And for this reason, much in the same way as before, velocity is defined as, can be presented as an equation in the form of change of displacement covered per unit interval of time. Now, here it must be highlighted that speed is a quantity that depends on distance, and since distance is a scalar, it makes sense to define speed as a scalar itself. On the other hand, velocity is a quantity that just so happens to depend on displacement. In that scenario, velocity just so happens to be a vector quantity. Now, notice how I use the same symbol for both speed and velocity. This is just a matter of notation really, or just a matter of convention, because especially in AS level physics, we'll be dealing with linear motion. More specifically, all these definitions that we're writing right now, they were first presented for linear motion. For this reason, when it comes to linear motion, we are dealing with objects that are moving in a straight line. So that would be an object starting from A, stopping at B, and let's say they're moving like so. In that scenario, notice how distance and displacement just so happen to be the same thing, which is why if you measure how they're changing with respect to time, they just so happen to be the same thing. In that case, what we're showing is that velocity and speed are pretty similar. So the only difference between the two is that velocity is nothing but a speed with direction. So this is just a simple thing to keep in mind, but it will help us especially when it comes to solving more complicated questions as they appear later on. Now we have another quantity we should introduce, that is acceleration. Acceleration is what we define as the rate of change of velocity. So you're simply seeing how velocity itself is changing with respect to time. The equation is quite straightforward. The symbol we'll be using for acceleration is A, and it's equal to a change in velocity over an interval of time delta t. This change in velocity can also be expressed as the final velocity v minus initial velocity u over some time interval delta t. And it's usually going to be this formula that we'll be most accustomed to. Now, all of these quantities that we've defined so far, they're all well and good. But what about an object that's moving in a far more complicated path? Let's suppose you have that same observer moving from A, stopping at B momentarily, and then landing at C. And what if they're moving in an even more complicated path? Let's say they're moving like this between A and B, and then from B to C they move in a straight line. Now, when you have this kind of a complicated kind of motion, we want to understand quantities in averages. In that regard, one average quantity that we are familiar with and should be able to use is average speed. Average speed is pretty similar to speed. The only difference is that you're averaging it over the complete journey. So, where speed is something as distance covered per unit time, average speed becomes total distance covered per unit or divided by total time covered in the journey itself. So, we have presented all of our fundamental definitions, and now we wish to understand it better through a simple theory question. Pause. And that theory question goes as follows. Explain how is it possible for a car to travel a certain distance and yet have zero displacement. Now, this is a very specific question if you think about it. It seems quite simple, but it is a little bit tricky. You want there to be a certain path that an object can cover such that it has a non-zero distance, but at the same time has zero displacement. Now, for such a path, we want to be able to explain it. Now I want you to pause this video for a moment and give this question a try. I want you to think of one possible path that you could describe such that it has a non-zero distance with it but has zero displacement at the same exact time. Now, pause this video, give it a try, and we'll be right back. You're done? Well, keep your answer with you and let us first discuss this together and let's see if you got it right or not. Now, let's look at both these scenarios individually first. You want the distance to be non-zero. That would only happen if the path itself is quote-unquote non-zero. That would only be possible if the car were moving. So you know for a fact that the car has to move from some particular point. Now, if you want the displacement to be zero, while the car itself is also moving, you can't have the car be stationary anymore. In which case, we raise the question, how do we insist that displacement should be zero? For this, we really need to just go back to our definition of displacement itself. More specifically, a diagrammatic representation that we had done. You may remember we had drawn it as a starting point A, ending at B, and then a vector like arrow drawn from A to B. Now, imagine me picking up this point A and bringing it closer and closer to A. Notice how I'm merely making the vector arrow shorter and shorter. Imagine what happens if I place A and B at the same exact point. What I've drawn is basically a zero vector. Now, how would the starting and ending points be the same? That would only happen if the car were moving from one point, let's say that's starting point, all the way and must return back to that ending point. So diagrammatically, that would look something like this. You have a car starting from A, covers some path and returns back at A. Notice how the car itself is covering some non-zero path, which means distance is non-zero, and at the same time has zero displacement since the starting and ending points are overlapping. And so you have a path that's been described in such a way that it has non-zero distance but zero displacement. And so we have landed at the ending of our first checkpoint. We've introduced some fundamental definitions, and now we have a better understanding of them. I want you to revisit these definitely, understand them a bit more conceptually, so that next time when we dive into different types of motion and how we can describe them, we'll have a better understanding of these together. Thank you. Welcome back. I'm Mahnur, and today we will be continuing on with the chapter of kinematics.